Okay, in this section we're going to be working on related rates, which is using implicit differentiation in real-life situations to solve for the rate of something. So first we are just going to start with a conical tank. When water is drained out of a conical tank, the volume, the radius, and the height are all functions of time t, which means we have to do everything with respect to t. So in the last section when we were doing implicit, we had to do dy dx. Everything here is going to be whatever variable it is, dt. So if we take the derivative of this volume equation, dv dt equals pi over 3 times 2r dr dt h plus pi over 3 dh dt times r squared. That was the product rule. So as you can see, we have three different rates, dv dt, dr dt, and dh dt, all of them related to one another. This one we're not actually asking the question, I just wanted to show you how we were going to do all of the dv dt's, etc. So we're going to actually move on to a problem we're going to solve for something. We have x and y, and they're both differentiable of t, which means they're going to be with respect to t, and they're related by the equation y equals x squared plus 3. Find dy dx when x is 1, given that dx dt is 2 when x is 1. So we need to figure out what we know and what we need to find out. We know that dx dt is 2, and we want to find dy dx. We know that x is 1 as well. So we're going to take the derivative of our equation, y equals x squared plus 3. So we have dy dt equals 2x dx dt. And that's it. The 3 goes away. So we know dx dt is 2, and x is 1. We're trying to find what dy dt is. 2 times 1 times 2 is 4. So we just have to figure out what we know, what we need to find out, and it's usually just as simple as take the derivative and plug stuff in. Alright, ripples on a pond. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, find the rate. At what rate is the total area of the disturbed water changing? So we know that we have the radius and the area, and we know that they are related by the area formula for a circle, which is pi r squared. We know dr dt, that's the rate of change of the radius, is 1 when the r is 4. We're trying to find dA dt. So we're going to take the derivative of our area formula. dA dt equals pi times 2r dr dt. So dA dt is pi times 2 times 4 times 1, which is 8 pi foot per second. It's the area, so it's foot squared per second. Okay, let's go quick over the guidelines of how we do related rates problems. First, we have to identify what's given and what's to be determined. We've done that already. Make a sketch if you need to and label all the quantities. Write an equation which relate all of our variables to one another. Then we use the chain rule to implicitly differentiate both sides with respect to time t, as I have said. And then we put in everything that we know and solve for which one we're looking for. Okay, we're going to skip this little section. Move on to the inflating balloon. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So we are given the rate that the air is being pumped into the balloon. So we know that's volume. And that's 4.5. We need to find the rate of change of the radius when our radius is 2. So we have to think about what relates our radius and volume of a sphere. That would be 4/3 pi r cubed. If we take the derivative of 4/3 pi r cubed, it's dv dt equals 4/3 pi times 3r squared dr dt. And then from there we plug in everything that we have been given, which is dv dt, r, we need to find dr dt. So we're going to do 4.5 divided by 16 pi. And we're going to approximate that to 9/100ths per minute. And we know the label is just in feet because we're just looking at the rate of change of the radius. So it's not squared or cubed. Okay, the speed of an airplane tracked by radar. An airplane is flying on a flight path that will take it directly over a radar tracking station. If s is decreasing at a rate of 400 miles per hour when s is 10, what is the speed of the plane? So first, we don't know what s is. This picture would be given with the problem. It's just a little challenging to put all these pictures in the problems for this specific format. So we are given s is 10. How are we going to find what x is? Because x is going to be the flight path of the plane. So we need to find what that is. We're going to find that using Pythagorean theorem when x is 10. So the Pythagorean theorem in this case is this formula, which is what we're going to use to relate all three of our sides. And first we're going to plug in 10 to find out what x is. In this case, x is 8. So we are given s is decreasing, that's ds dt, and if it's decreasing, that means it's negative, so it's negative 400. When s is 10, we are trying to find the other variable is dx dt when s is 10. Okay, so we need to take the derivative of our Pythagorean theorem here. 2x dx dt, 6 squared goes away, equals 2s ds dt. We plug in everything that we know. X is obviously 8, we just found that. Dx dt is what we're trying to solve for. S is 10. Ds dt is negative 400. So dx dt, when everything is divided and simplified, is negative 500. But because negative is telling us that's direction, so that's velocity, so really we want to use positive 500 miles per hour since we're trying to find speed, and speed is the absolute value of velocity. Okay, find the rate of change in the angle of elevation of a camera at 10 seconds after liftoff. Well, we need another picture. So here we're going to have a little camera. This picture would be given to you as well. You're never expected to come up with the picture unless it's a basic one that we know. Our rocket's up here. Our angle's right here. We are given that this is 2,000 feet. We are given the relationship between theta and s, which is a tangent of those two. And we are given that s is 50 t squared, where t is theta, height is s equals 50 t squared. And when t is 10 seconds, that's 50 times 100, which is 5,000 feet. We are given ds dt is 100t, because we have s is 50t squared, so the derivative of that is 100t. That's our velocity. We need to find d theta dt when our time is 10 and our position is 5,000. So the relationship we're going to use between these two variables is our tangent. Tangent of theta equals s over 2,000. Take the derivative of that. Derivative of tangent is secant squared. And derivative of s is just ds dt. And the 1 over 2,000 is just a constant, so that stays there. And we want to solve, whoops, we need a d theta dt over here. Since we want to solve for d theta dt, we need to get rid of that secant squared. If we divide by secant squared, it becomes cosine squared on the other side. So cosine squared theta, we know that ds dt is 100t. Then we have that 2000. We're going to know that cosine theta is 2000 over the square root of s squared plus 2000 squared from the Pythagorean theorem, looking at the picture we have. So if we plug that in, d theta dt equals 2000 over the square root of s squared plus 2000 squared, whole thing is squared, times 100t over 2000. When t is 10 and s is 5000, again, that's just stuff that we know already that I'm rewriting down here. Plug in everything, d theta dt equals 2000 over square root of 5000 squared plus 2000 squared times 100 times 10 over 2000. And if we simplify all that, we're going to come out to 2/29ths radians per second, and we know that our label is going to be in radians because we're measuring an angle. Okay, we're actually going to skip this last problem as well, and just talking about the homework assignment, instead of starting at 14, we're going to start at 16, and we're going to skip the last problem. So that is related rate, section 2.6.